Welcome to this lesson on orbital motion. Today we'll explore one of the most fascinating topics in physics, how satellites and planets stay in orbit. We'll discover the invisible forces that keep objects circling around Earth and other celestial bodies without falling down or flying away into space. Let's start with a fundamental question. Why don't satellites fall back to Earth due to gravity? And why don't they simply fly off into the vastness of space? The answer lies in a delicate balance of forces. Satellites are constantly falling toward Earth, but they're also moving forward fast enough that they keep missing it. This creates a curved path that we call an orbit. The key to understanding orbits is centripetal force. Centripetal means center-seeking. For objects in orbit, gravity acts as this centripetal force. It constantly pulls the satellite toward the center of Earth, preventing it from flying off in a straight line. Without gravity providing this inward force, the satellite would obey Newton's first law and continue moving in a straight line into space. So gravity isn't just pulling things down. It's actually keeping satellites up in orbit by continuously changing their direction. For a stable orbit, there's a perfect balance that must be achieved. The gravitational force pulling the satellite inward must exactly equal the centripetal force required to keep it moving in a circle. We express this balance mathematically by saying that gravitational force equals centripetal force. This simple equation is the foundation of all orbital mechanics and helps us understand everything from satellites to planets to entire solar systems. Let's look at the gravitational force in detail. The force of gravity between two objects equals g times m divided by r squared. Here, g is the universal gravitational constant, a fundamental number in physics. M is the mass of the central body, like Earth. M is the mass of the orbiting object, such as a satellite, and r is the orbital radius, the distance from the center of Earth to the satellite. Notice that as the distance r increases, the gravitational force decreases rapidly, because r is squared in the denominator. Now let's examine centripetal force. For any object moving in a circle, the centripetal force equals m times v squared divided by r here. M is again the mass of the orbiting object. V is the orbital velocity, how fast the satellite is moving along its circular path. And r is the orbital radius. This force is always directed toward the center of the circle, constantly changing the object's direction to keep it moving in a curved path rather than a straight line. Now comes the crucial step. For a stable orbit, we set these two forces equal to each other. Gravitational force equals centripetal force. This gives us g times m divided by r squared equals m times v squared divided by r. This equation tells us exactly what conditions are needed for an object to maintain a stable circular orbit. It connects the properties of the central body, the orbital radius, and the required velocity. By solving the previous equation for velocity, we obtain the orbital velocity formula. The velocity needed for a stable orbit equals the square root of g times m divided by r. This elegant equation tells us the exact speed a satellite must travel to orbit at a given distance r from a central body of mass m. Notice something remarkable. The mass of the satellite itself doesn't appear in this formula. This means that whether it's a small satellite or a massive space station, they both need the same speed to orbit at the same altitude. Let's highlight three important insights from our orbital velocity formula. First, orbital velocity is independent of the satellite's mass. A tiny CubeSat and the International Space Station need the same speed at the same altitude. Second, closer orbits require higher speeds. Satellites near Earth must travel faster to avoid falling. Third, farther orbits require lower speeds. The Moon, which orbits much farther from Earth, moves much more slowly than satellites in low Earth orbit. This inverse relationship between distance and speed is fundamental to understanding orbital mechanics. To summarize, we've discovered how orbital motion works. Gravity provides the centripetal force that keeps satellites and planets in stable orbits. By balancing gravitational force with the requirements of circular motion, we can calculate exactly how fast an object must travel to orbit at any given distance. This beautiful interplay between gravity and motion governs everything from artificial satellites to the planets orbiting our sun. Understanding these principles is essential for space exploration, satellite technology, and our comprehension of the cosmos.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.